the vast, silent expanse of space, a canvas painted with billions of stars. For centuries, humanity has gazed upwards, a primal question echoing in our collective consciousness: are we truly the only ones? Today, that question is no longer confined to the realm of science fiction. It's a burning inquiry at the forefront of scientific exploration, a puzzle that brilliant minds are meticulously piecing together. And the answer, whispered on the solar winds and etched in the cosmic microwave background, is leaning more and more towards a resounding: we are likely not alone. Welcome to a journey that will challenge your perception of our place in the universe. For generations, the idea of extraterrestrial life has been a source of wonder, fear, and endless speculation. But what if I told you that the evidence, the scientific data, the very laws of physics themselves, are pointing us towards a universe teeming with possibilities? This isn't about little green men in flying saucers, at least, not primarily. This is about the profound implications of astrobiology, exoplanet discoveries, and the tantalizing hints that life, in some form, might be far more common than we ever dared to believe. We're going to delve into the groundbreaking work of scientists who are actively searching for answers. We'll explore the incredible technologies that allow us to scan distant worlds, analyze their atmospheres, and even listen for the faintest whispers of alien intelligence. We'll unpack the fundamental requirements for life as we know it, and then we'll venture into the mind-bending scenarios where life might exist in forms we can barely comprehend. Think about it. Every day, new planets are discovered orbiting stars light years away. Many of these exoplanets reside in the habitable zone, that sweet spot where liquid water, the universal solvent for life on Earth, could potentially exist. We're talking about worlds with oceans, with atmospheres, with the building blocks of life already present. Is it truly so outlandish to suggest that in some of these countless cosmic cradles, life has indeed taken root and flourished? This video isn't about definitive proof. The universe is a vast and complex place, and definitive proof is notoriously difficult to come by. Instead, it's about the compelling convergence of scientific disciplines, the mounting probability, and the sheer, exhilarating that we are part of something much, much larger than we ever imagined. It's about understanding the scientific reasoning behind this growing conviction, the observational evidence that fuels it, and the ongoing quest that promises to reshape our understanding of life itself. So, buckle up. We're about to embark on an expedition into the very heart of the alien question, and by the end of this journey you'll understand precisely why so many scientists are no longer asking we're alone but rather, and we might find our cosmic neighbors. This is the compelling case for why scientists believe we are not alone. Ting towards a universe teeming with life? Today, we're diving deep into the compelling reasons why scientists, armed with cutting-edge technology and a rigorous pursuit of knowledge, increasingly believe that Earth is not the sole sanctuary of life. We'll explore the mind-boggling numbers that suggest life should be abundant, the tantalizing discoveries of exoplanets in habitable zones, the intriguing possibilities of life arising in extreme environments here on Earth, and the ongoing ambitious searches that could one day provide definitive proof. Prepare to have your cosmic perspective expanded, because the universe is far grander, and potentially far more populated, than you might ever have imagined. A universe of potential. Let's start with the sheer scale of it all. When we talk about the universe, we're not talking about a few thousand stars or even a few million. We're talking about numbers so astronomically large they defy easy comprehension. Our own Milky Way galaxy, a single island in the cosmic ocean, contains an estimated 100 to 400 billion stars. Let's be conservative and say 200 billion stars. Now, consider that the observable universe, the portion we can currently detect, contains an estimated 2 trillion galaxies. That's 2 galaxies, each with hundreds of billions of stars. If you try to multiply those numbers, you get a figure so colossal it's almost meaningless. We're talking about septillions of stars, a 1 followed by 24 zeros. To put that into perspective, if you could count one star every second, it would take you longer than the current age of the universe to count all the stars in the observable universe. It's a number so vast that even the most pessimistic estimates of life's probability become almost irrelevant. The fundamental argument here is one of sheer statistical probability. If life arose on Earth, a planet orbiting an average star in a typical galaxy, why wouldn't it arise elsewhere? To believe we are alone requires us to assume that the conditions that led to life on Earth are extraordinarily rare, so rare that they've only occurred once in this unfathomably vast cosmic arena. Scientists, by their very nature, tend to favor explanations that are not based on extreme improbability. The simpler, and in this case, more statistically likely explanation, is that life is a natural, perhaps even common, outcome of the universe's fundamental processes. Imagine finding a single grain of sand on a beach. If that beach had only 10 grains of sand, finding one would be remarkable, perhaps even unique. But if that beach has trillions upon trillions of grains of sand, finding one grain of sand that's a particular color or shape is not remarkable at all, it's statistically inevitable. The universe, with its septillions of stars, is that unimaginably vast beach. The Drake equation, formulated by astronomer Frank Drake in 1961, attempts to quantify the number of active, communicative extraterrestrial civilizations in our galaxy. While many of its variables are still unknown and subject to educated guesswork, it provides a framework for thinking about the factors involved. N equals R asterisk XFP XNE XFL X5 XFC XL, the average rate of star formation in our galaxy. Asterisk, the fraction of those stars that have planets. Asterisk, the average number of planets that can potentially support life per star that has planets. Asterisk, the fraction of planets, capable of supporting life, that actually develop life at some point. Asterisk, the fraction of planets with life that go on to develop intelligent life. Asterisk, the fraction of civilizations that develop a technology that releases detectable signs of their existence into space. Asterisk, the length of time for which such civilizations release detectable signals into space. Even with conservative estimates for some of these variables, the equation can yield a surprisingly large number for n, the number of civilizations we could potentially communicate with. For instance, if we assume that there are 100 billion stars in our galaxy and that 10% of them have planets, and that each of those systems has on average 2 planets in the habitable zone, and then we get very conservative with the remaining factors. Say only 1 in a billion planets develops life and only 1 in a billion of those develops intelligent life and they last for 1,000,000 years. Even with these incredibly conservative numbers, the result for n could still be in the thousands, or even millions. The point isn't to get an exact number, but to illustrate that even with low probabilities, the sheer scale of the universe makes the existence of other life, and even other intelligent life, a statistically plausible outcome. Worlds within reach for most of human history, we only knew of the planets in our own solar system. The idea of planets orbiting other stars was pure speculation. But in the last few decades, our understanding has exploded. The discovery of exoplanets, planets outside our solar system, has revolutionized astronomy and significantly bolstered the case for extraterrestrial life. We now know that planets are not rare exceptions, they are the norm. The Kepler Space Telescope, and now missions like TESS, have revealed that most stars in our galaxy host planets. In fact, current estimates suggest there are more planets in the Milky Way than there are stars. This is a profound shift in our cosmic perspective. We're not just looking at a galaxy of stars, we're looking at a galaxy of star systems, each with its own retinue of worlds. But it's not just about the sheer number of planets, it's about the of planets we're finding. Scientists are particularly interested in exoplanets that reside within the habitable zone of their stars. This is the region around a star where the temperature is just right for liquid water to exist. On the surface of a planet, liquid water is considered essential for life as we know it, acting as a solvent for biochemical reactions and a medium for transport within cells. We've discovered thousands of exoplanets, and a significant fraction of these are rocky, Earth-sized planets located within their star's habitable zone. For example, the TRAPPIST-1 system, located about 40 light-years away, has 7 Earth-sized planets, several of which are believed to be in the habitable zone. While we don't know if these planets actually have water or atmospheres, their existence demonstrates that planets with the potential for habitability are not just theoretical constructs. They are out there, waiting to be discovered. The diversity of exoplanets is also fascinating. We've found gas giants, ice giants, super-Earths, and mini-Neptunes. While some of these might not be ideal candidates for life as we know it, their existence suggests a rich variety of planetary environments where life might find a niche. Some scientists even speculate about life existing in subsurface oceans on icy moons, similar to Europa or Enceladus in our own solar system, or even in the atmospheres of gas giants. The search for biosignatures on exoplanets is the next frontier. Biosignatures are gases or combinations of gases in a planet's atmosphere that could indicate the presence of life. For example, the simultaneous presence of oxygen and methane in an atmosphere is considered a strong potential biosignature, as these gases tend to react with each other, and would likely need to be continuously replenished by biological processes. Telescopes like the James Webb Space Telescope are now capable of analyzing the atmospheres of exoplanets, opening up the possibility of detecting these crucial indicators. While we haven't found definitive biosignatures yet, the technology is rapidly advancing, and the number of promising targets is growing. The earthly proof if we're looking for life elsewhere, it's helpful to consider the incredible resilience and adaptability of life right here on Earth. For a long time, scientists assumed that life needed very specific, temperate conditions to thrive. They imagined life existing in sunlit oceans, perhaps in shallow pools. But discoveries in recent decades have shattered these assumptions, revealing that life can exist in environments that we would consider incredibly hostile. These organisms are known as extremophiles. They thrive in conditions that were once thought to be utterly incompatible with life. Deep on the ocean floor, miles below the surface, in complete darkness, where superheated, mineral-rich water spews from the Earth's crust. These environments are under immense pressure and are devoid of sunlight. Yet, complex ecosystems, powered by chemosynthesis, flourish around these vents, supporting unique bacteria, archaea, and even larger organisms like tube worms and crabs. This is a powerful analogy for potential life on ocean worlds like Europa or Enceladus, which are thought to have subsurface oceans heated by tidal forces. Some bacteria and archaea can survive in highly acidic conditions, like those found in some volcanic springs or industrial waste, with pH levels comparable to battery acid. Others thrive in highly alkaline environments, such as soda lakes. Deinococcus radiodurans * can withstand doses of radiation thousands of times higher than humans. We have thermophiles that live in boiling hot springs and geysers, and psychrophiles that survive in sub-zero temperatures in polar ice and deep-sea sediments. Some organisms are adapted to live under immense pressure in the deepest parts of the ocean trenches, where the pressure is hundreds of times greater than at the surface. Life has been found existing in seemingly barren desert soils and within highly concentrated salt crystals, demonstrating an ability to survive with minimal water. The existence of extremophiles on Earth demonstrates that life is not a fragile phenomenon confined to gentle, Earth-like conditions. It suggests that life can arise and persist in a much wider range of environments than we previously imagined. If life can find a way in the boiling volcanic vents of Yellowstone, the acidic lakes of Mexico, or the frozen deserts of Antarctica, then it's not unreasonable to think that it could find a way on other planets, or moons, even those that appear inhospitable to us. This has profound implications for astrobiology. It means that when we search for life beyond Earth, we shouldn't be limited to looking for planets that perfectly mirror Earth. We should also consider moons with subsurface oceans, planets with thick, exotic atmospheres, or even environments that seem entirely alien to our terrestrial sensibilities. The lessons learned from extremophiles suggest that life is tenacious and adaptable, capable of exploiting even the most challenging niches. Furthermore, the study of extremophiles also informs our understanding of the origins of life itself. If life can arise in such diverse and extreme conditions, it suggests that the initial spark of life might have occurred in similarly challenging environments on early Earth, perhaps around hydrothermal vents, or in volcanic hot springs rather than solely in warm shallow ponds. This broadens the scope of where and how life might have begun, both on our planet and potentially on others. Listening and looking, the scientific community isn't just theorizing about extraterrestrial life, they are actively searching for it. This search takes many forms, from listening for signals from intelligent civilizations to directly searching for microbial life within our own solar system. For decades, projects like SETI have been scanning the skies, using radio telescopes to listen for artificial signals that might be broadcast by intelligent alien civilizations. These signals, if detected, would be unmistakable evidence of technological life beyond Earth. While no definitive signals have been found yet, the search continues with increasingly sophisticated instruments and broader sky coverage. Projects like Breakthrough Listen are using powerful telescopes to survey millions of stars, looking for narrowband radio signals or optical pulses that could indicate an alien technology. The sheer amount of data collected is immense, and the analysis is ongoing. Within our own solar system, Mars is a prime target in the search for past or present microbial life. Rovers like Curiosity and Perseverance are equipped with instruments to analyze Martian rocks and soil, searching for organic molecules and signs of ancient water. The discovery of evidence for liquid water on Mars in its past, and the ongoing presence of subsurface ice, makes it a compelling candidate. Beyond Mars, the icy moons of Jupiter and Saturn, Europa and Enceladus, respectively, are generating immense excitement. Both moons are believed to harbor vast subsurface oceans of liquid water beneath their icy crusts, kept liquid by tidal heating from their parent planets. These oceans are considered potentially habitable environments, and future missions are being planned to explore them. The Cassini mission, for example, detected plumes of water vapor and ice particles erupting from Enceladus's south pole, suggesting that material from its subsurface ocean is being ejected into space, offering a potential opportunity to sample its contents without even drilling through the ice. As mentioned earlier, the James Webb Space Telescope is already a game-changer in exoplanet research, allowing us to analyze their atmospheres for biosignatures. Future generations of telescopes, both ground-based and space-based, will offer even greater capabilities, enabling us to study smaller planets, analyze atmospheres in greater detail, and potentially even image exoplanets directly. The quest for life beyond Earth is driving innovation in telescope design, detector technology, and data analysis techniques. The search is a long game. It requires patience, persistence, and significant investment. But the potential reward, the discovery of life beyond Earth, would be one of the most profound scientific discoveries in human history, fundamentally altering our understanding of life and our place in the cosmos. A cosmic reckoning. If scientists are increasingly confident that we are not alone, what does that mean for us? The implications are staggering, touching upon philosophy, religion, science, and our very sense of identity. The discovery of extraterrestrial life, even microbial life, would prove that life is not a unique fluke of Earth but a natural phenomenon that can arise elsewhere in the universe. This would challenge our anthropocentric view and force us to reconsider our place in the grand cosmic tapestry. We would no longer be the sole inhabitants of a vast and empty universe, but one species among potentially many. The study of extraterrestrial life, its biochemistry, its evolution, and its potential technologies, would undoubtedly lead to unprecedented scientific breakthroughs. Understanding how life arises and functions in different environments could revolutionize biology, medicine, and our understanding of the fundamental laws of nature. If we were to encounter intelligent life, the exchange of knowledge could accelerate human progress in unimaginable ways. For millennia, human belief systems have often placed humanity at the center of creation. The discovery of other life forms, particularly intelligent ones, would undoubtedly prompt deep reflection and re-evaluation within religious and philosophical traditions. While some faiths might find ways to incorporate this new reality, others might face significant challenges. It would force us to confront fundamental questions about consciousness, intelligence, morality, and the purpose of existence. The concept of the Great Filter is a potential explanation for the apparent paradox of why we haven't detected widespread evidence of advanced extraterrestrial civilizations, despite the high probability suggested by the Drake equation. The Great Filter posits that there must be some extremely difficult or improbable step in the evolution of life from simple beginnings to a starfaring civilization. This filter could lie in our past or in our future, If the filter is in our future, the discovery of simple microbial life elsewhere might be a cause for concern, suggesting that the transition to complex or intelligent life is the challenging step. Conversely, finding evidence of advanced civilizations would suggest the filter is behind us. Ultimately, the belief that we are not alone is not based on definitive proof, but on a convergence of scientific evidence and logical reasoning. The vastness of the universe, the ubiquity of planets, the resilience of life, and the ongoing advancements in our detection capabilities all point towards a universe that is likely teeming with life. The question is no longer we will find evidence, but and that evidence will take. The journey of discovery is ongoing, and with each new observation and each new mission, we get closer to answering that most ancient and profound question. The universe is vast, mysterious, and full of possibilities, and the scientific community is diligently working to unravel its secrets, one star system at a time. The implications of finding even the smallest sign of life beyond Earth would be monumental, forever changing our perspective on our place in the cosmos and the very definition of life itself. The scientific endeavor to answer, "Are we alone?" is one of the most compelling and exciting quests humanity has ever undertaken, pushing the boundaries of our knowledge and inspiring us to look further, listen closer, and dream bigger about the universe we inhabit. So, as we've journeyed through the cosmos, from the icy moons of our own solar system to the furthest reaches of exoplanetary discoveries, the evidence has painted a compelling, if still incomplete, picture. We've seen how the building blocks of life, water, organic molecules, are not unique to Earth, but are scattered across the universe like cosmic dust. We've marveled at the sheer abundance of planets, billions upon billions, each a potential cradle for life. We've considered the tenacity of life itself, thriving in environments on Earth once thought utterly inhospitable, suggesting it could find purchase in countless alien worlds. And we've explored the tantalizing possibilities presented by the Fermi paradox and the Great Filter. Is the silence deafening because life is rare, or because something inevitably silences civilizations before they can reach out? The discovery of simple microbial life elsewhere might indeed suggest that the real hurdle, the true Great Filter, lies in the evolution of complex or intelligent life. Conversely, if we were to stumble upon evidence of advanced civilizations, it would imply that the most difficult evolutionary leaps are behind us, that the universe is perhaps more populated with sentient beings than we currently dare to imagine. The search continues, fueled by an unyielding curiosity and the relentless march of scientific innovation. From the James Webb Space Telescope peering into the atmospheres of distant exoplanets, searching for biosignatures, to the ongoing efforts to detect technosignatures from potential alien intelligences, we are developing ever more sophisticated tools to listen to the universe's whispers. Our understanding of astrobiology is expanding, our engineering capabilities are soaring, and our collective imagination is being stretched to its limits. The belief that we are not alone is not a leap of faith, but a conclusion drawn from the best available scientific data and the most reasoned logical deductions. The universe is a stage of unimaginable scale, and it seems improbable, statistically speaking, that life's grand experiment has played out only once, on our solitary blue marble. The question, therefore, is not a matter of we will find evidence of extraterrestrial life, but that evidence will emerge, and in what astonishing form it will present itself. Will it be the faint chemical signature of microbes in an alien ocean? Or perhaps a structured signal, a deliberate message from a distant star? This journey of discovery is not merely an academic pursuit, it is a fundamental human endeavor. It pushes the boundaries of our knowledge, challenges our preconceived notions, and inspires us to look beyond our terrestrial home. The implications of finding even the smallest, simplest sign of life beyond Earth are profound. It would rewrite our textbooks, reshape our philosophies, and irrevocably alter our understanding of our place in the grand tapestry of existence. It would mean that life is not a cosmic fluke, but a natural, perhaps even common, phenomenon. The scientific community, driven by this profound quest, is diligently working, day and night, across observatories and laboratories, to unravel these cosmic secrets. We are listening to the faint hum of distant galaxies, analyzing the light from alien suns, and exploring the potential havens within our own solar system. Each new observation, each successful mission, brings us a step closer to answering that most ancient